Hi, I'm Mahika. We're the QCY group, and this is our presentation on using quantum machine learning to improve the detection of spinal injuries, defects, and illnesses. Starting off with the abstract, Alyssa's going to tell you guys what our research touches on.
So to give a brief overview of our research targets osteoarthritis, the abnormal growth, damage, and gradual degeneration of connective tissues, which then relates to osteophytes, foraminal stenosis, and other forms of vertebrae misalignment or collapse that are detectable through MRI and are the main types of spinal injuries that are included in our data sets. And by using a quantum convolutional neural network and visual transformer, we aim to optimize classical computing solutions by taking advantage of the increased complexity, compression, and precision of quantum computing.
Yeah, and a little background information. Like Alyssa said, one of the primary conditions our research focuses on is osteoarthritis. This is a spinal condition that involves the gradual degeneration of cartilage, tendons, ligaments, and any other connective tissues. And while this condition does not have a specific cause yet, it's most common in women over the age of 50 or people with joint injury, abnormalities, or any relevant genetic impacts. And while I said this condition doesn't have any specific cause, there are some common factors like obesity, a family history, or any past injury/surgery, the overuse of joints, and abnormal tissue development. Some symptoms of this condition include pain, stiffness, swelling, along with limited movement. Another side effect of this condition includes osteophytes or bone spurs. These are essentially small bone growths that form around joints damaged by arthritis, and they are detectable by X-ray, which is how we were able to identify this condition in our research. Some treatments for this condition include painkillers, physiotherapy, weight loss, along with surgery. Moving on to our literature review, obviously we used many sources while conducting our research. However, these are just a couple. Starting with the very beginning, we had to first retouch on what the spine does and like the different parts. The different parts obviously include the spinal cord and the vertebral column. And the purpose of the spine is to send messages between the brain and the rest of the body to control movements, sensations, and reflexes, which is why it's such a problem when there's impairments and conditions with the spine. Speaking of injuries and spinal conditions, spinal cord injuries, or SCIs, are classified on a scale of A to E, with A being complete and total impairment of the spine, and E being a normal functioning spine. The different segments of the spine these injuries can occur on include the cervical, thoracic, lumbar, and sacral segments of the spine. Now, moving on to our situation and problem statements.
All right, let's talk about the current situation and the problems that motivated our research. So the current situation right now is that the complexity of incorporating machine learning models in the biomedical imaging field leaves many areas that have yet to be thoroughly and specifically researched, such as the classification of MRI images of spinal cords and injuries. And the general research process flow that we will be going through is first the data set, which we'll explain in a bit, which we used a free public data set that contains 10,466 manually classified scans of 13 different spinal abnormalities. And uh, and then the 7-layer convolutional neural network that we will use later that distinguishes black on white and white on black images and alters them accordingly. And then we have the quantum part of our research, where data is run through a quantum convolutional neural network and quantum vision transformer pipeline. for feature extraction and contextual understanding. All right, so the problems that we that like motivated our research were that spinal cord injuries can be ambiguous to classify with the human eye, which can lead to different identifications from different doctors, and it can lead to biases. So machine learning can fix these biases by giving unbiased, consistent identifications. So let's talk about the objectives. So our main objective of this research. So previously there were many studies using machine learning to detect spinal cord injuries, but they used traditional convolutional neural networks. In our research, we aim to develop a novel quantum convolutional network based machine learning model to detect and classify spinal cord injuries in patients using MRI scans. So talking more about the data set, again, we have 10,466 spinal, it should be MRI images, but yeah. So our data set is called the VinDR Spine XR dataset. We use 20% of the rate of the images for testing and 80% for training. And we do have we're using digital imaging and communications in medicine format, which is abbreviated as DICOM. So this is the format of the image, and they're all in grayscale, so black and white. For pre-processing, we're using pixel data arrays that are extracted from each DICOM file using the PyDICOM library, and we stored it in PNG form, or portable network graphics. Due to server memory limitations, we changed the 12-bit grayscale pixels to all to 8-bit, and images were resized to 400 by 400 pixels, in which rectangular dimensions were cropped and flattened by a percentage of the height with width ratio to prevent possibly cutting out crucial segments of the spine.
So our images from the dataset are pre-processed through multiple steps, including applying a histogram equalization algorithm and using pre-trained models to remove elements such as letter annotations and accessories or nearby bones that causes like imaging interference to make sure that the data set is cleaner. However, the main part of our pre-processing is using a color inversion CNN. So what this does is, because some images are, as you might have noticed on the previous slide, black on white, whilst other images are white on black, the CNN aims to standardize this and make sure that all of them are black and white. So this enhances color contrast for better distinction of negative and positive spaces, along with the histogram equalization. And also it ensures that the foreground and background color arrangements are consistent. So how the CNN works is that it will test on 750 image subsample for training, and then it will use that for training, and then it will test on 250 other images. So after the model is trained on those images and knows to identify whether the image is black on white or white on black, it will be used on the rest of the thousands of images in the data set. And after identifying which is which, we will invert pixel colors of images that are white on black so that they are black and white, and that has the effect of standardizing the images in the data set.
Okay, so we aim to first set a baseline of accuracies with the regular traditional CNNs and visual transformers before enhancing them with quantum. So we propose to use the CNN due to its usefulness for image recognition as it efficiently learns spatial hierarchy. CNNs use pooling layers to downsize feature maps and convolutional filters to extract spatial patterns. And as we continue to train our model, we will test different structures, such as the VGG16 or the VGG19, due to their simplicity. VGG16 has been widely used as a baseline model for various computer vision tasks due to its strong performance and ease of implementation. So it's a likely model that we will use to set as the baseline accuracy for our subsequent models. Other likely candidates are DenseNet and ResNet. And Liu demonstrated the potential of the, CNNs in where they used a multi-scale convolutional net to diagnose Alzheimer's disease, achieving an accuracy of around 98%. And as we further compare accuracies between structures, we also will compare the CNN results with vision transformers. So vision transformers lack the inductive bias of translation invariance, meaning they can detect an object regardless of appearance or position. And they're typically trained on large data sets, needing several million images to compare to CNNs. And so we propose to train the visual transformer on our data set and also compare it with visual transformers first pre-trained on larger data sets such as ImageNet before testing it on ours. So a Siri used pre-trained visual VIT-B32 to detect brain tumors with an accuracy of 98.24%. So we will be testing this VIT-B32, which has 12 transformer encoder layers with 32 attention heads. And this was we will fine-tune this model after training it on the ImageNet dataset to focus on our task. And including the VIT B32 shown, we will also use the contrastive language image pre-training, which can learn visual representations from images and textual representations from associated captions. And finally, the DEET is a variant of visual transformers designed for data efficient training, making it suitable for scenarios with limited label data, which can be the case for our data with class imbalances between different injuries and less than 1 million images. And testing original models with accuracy, recall, and cross-validation before improving them with quantum to observe the differences.
So we aim to enhance our medical image analysis by incorporating quantum machine learning. And basically, it uses principles of quantum computing where there are qubits which can exist in multiple states simultaneously, also known as superposition. And then entanglement allows these qubits to be correlated because bits which are in states of 0 and 1 generally can be correlated, but then in quantum entanglement, the state of one qubit can depend on the other. And so by using this combination, it allows us to efficiently process the large amount of medical data that comes with like MRI data sets. And then by having these states of qubits correlated, we are able to develop more accurate and reliable models. So then specifically in spinal injury detection, we can utilize quantum convolutional neural networks, or QCNNs, and quantum visual transformers. So then QCNNs use like parallelism to extract features and detect abnormalities, as you mentioned, using qubits, while quantum visual transformers are able to process information across the multiple pixels at once. So it enhances the process, and then it's able to provide precise location of injuries. So by combining QCNNs and QVTs, we can optimize the accuracy of our spinal detection model. And the benefits of quantum computing are that it'll aid us in processing these large data sets efficiently, and it'll have more precision compared to regular CNNs or models.
So our research has a lot of significance in the healthcare industry. So the use of these models can lead to quicker and easier detection of spinal cord injuries, as the image analysis step will become automated. And this helps to reduce the amount of time needed for manual analysis by experts. And also these models will be consistent and standardized, so that will help with more reliable results. And also, these models can pick up on features that many experts may miss. So this can help with early detection of spinal cord injuries or abnormalities. And as mentioned earlier, so it's more reliable and consistent outcomes diagnoses. So it'll be trained and tested on a lot of data, so the results will be more consistent. And this is also more accessible and cost effective for healthcare providers, as diagnoses can be more remote. And also, these models can process high volumes of data, so patients can get their results back a lot faster. And it reduces the need for specialized expertise for image analysis and diagnosis. And finally, it also reduces the potential for errors or misdiagnoses. So this could be either system-related errors by machines or cognitive errors by incorrect information by the healthcare provider. So for our future work, we plan on finishing up our color inversion using a CNN for that. So right now a lot of our images are either black on white or white on black. So we plan on standardizing the images using a color inversion CNN. So once all the images are standardized, we will begin training and implementing classical CNN for spinal injury detection. So we will start with we'll train it on our pre-processed images that will be standardized, and then we plan on testing it and recording accuracy. And then eventually we also want to move on to QCNNs and for better accuracy and results. So we would like to thank ASDRP for giving us the opportunity to conduct this research, and also to Dr. McMahon for advising and guiding us throughout our research. And also finally to the QCX research group, as they helped us out a lot in answering questions in our pre-processing steps. So these are our references.
And that's our presentation. If anybody has any questions, now would be the time to ask.